All right. So we calculated the z to be equal to negative 2.22. Now we have to figure out the p-value, and the p-value is going to be z less than the value we calculated. Let's go back one, two, and here we are. This is the distribution. The z we calculated came out to be right there. And if you remember, the definition of the p-value is as extreme as, and we had covered previously that as extreme as you take the test value and you move away from the mean being zero in this situation right here. So whatever your z is, you're going to get your z and move away. So if your z is positive, you're going to go up. If your z is negative, you're going to go down. But you also have to remember that you need to account for the other side of the area, because as extreme as, it's either or, both sides, meaning that if you calculate the blue area, you need to multiply by 2. If you calculate the yellow area, you need to multiply by 2. So coming back to our example, our z was negative, therefore the p-value is going to be z less than the negative value, and we have to multiply by 2. So that gives us a p-value of 0.0264, or 2.64%. Now, is that a probability that is small, and therefore the results we received were atypical, they were very rare according to the null hypothesis, or are they just regular values? Well, remember, to be able to come up with this conclusion, you need to compare it to alpha, and alpha being 5%. And since the probability we received is less than 5%, it means that the probability we received is a small probability, meaning that whatever we observed was a rare outcome, meaning that it should not have occurred if the null is true, if the company was really putting 100 grams or milligrams, I forgot. We should not have observed a sample as extreme as 92. And therefore, our statistical conclusion is going to be to reject the null hypothesis, and our research conclusion is going to be that we do not believe that the company is putting 100 grams. So let's follow up with the lecture. So once we reach the p-value, this means that the assumption of the company was true, that the assumption in the null hypothesis, that if that was true, if that assumption was true, there's only 2.64% chance to obtain a sample of 25 pill as extreme as the one we obtained. This probability is very small, and hence we are more likely to say that the assumption is not likely to be true, and hence we conclude that the company claim is not true. Therefore, step number 5, which was that we compare the p-value to alpha. Step number 6, we're going to reject the null hypothesis since the p-value came out to be less than alpha. And that gives us this step number 7. We have evidence suggesting that the claim of the company is not true. And based on the results, based on the sample we observed, we're leaning towards that the concentration used by the company is actually less than 100. Now, remember, the alternative hypothesis that does not specify if it's more than 100 or less than 100. It's just say it's different. But what you're going to do is you're going to use your results to reach a more specific conclusion. Since our results are saying 92 grams, which is less than 100, that is going to push us to have a conclusion that it's less than 100. So answering the research question using the approach, I can basically answer research question of this sort. Does men have a higher rate of LDL than women? Is the proportion of children with asthma higher in urban areas when compared to rural areas? Is the average CO exhaust from cars in Lebanon in compliance with the international guidelines of 120 ppt or not? So there's a range of questions that you can actually ask and answer using this approach. And that approach is the testing hypothesis. To answer this question, with what we covered so far, we have the basic tools to answer this question. And therefore, what we did is called the hypothesis testing approach. So, so here's another example, I guess. Before we start with the first step, we need to know what is the research question. An insulin pump is devised to maintain the blood sugar level at 100. I'm using again 100 here, but I apologize for that. but it has just have to serve. It is very important that the average diabetic subject using the pump will have a blood sugar of 100, not more and not less. Thus, the research question is, do people using the pump have an average sugar level of 100? Okay, so step number one, based on the research question, I have to write or devise a null hypothesis and alternative hypothesis. If you remember what I said about the null hypothesis take things at their face value. It's a declaration of innocence. It's a declaration that whatever we are looking at is innocent. In this scenario, it means that, yeah, the pump works. The pump actually stabilizes the blood sugar at 100. In other instances in the future, that is going to mean something also innocence, but a bit different than what we have here. All right, so later on we will see that this also will be a declaration of no difference. What matters is that you're going to write a null hypothesis with an equal sign, and you're going to also write it using a parameter. So see here, I wrote the null hypothesis mu equal to 100, but you just have to remember mu of what. So that is the mu of the blood sugar level for which population? Population of diabetic patients using the pump. You have to be specific so that you know what are you studying. All right, so this is the null hypothesis. The alternative hypothesis, as you remember, it has to be everything else, and therefore the alternative hypothesis mu is not equal to 100. Okay. Step number two. Oh, actually, this is just another example. Null hypothesis if you're comparing men to women. Don't worry about it. We'll come back to that when we start talking about two groups. All right, so the alternative hypothesis is not equal to 100. And I told you, I kind of like hinted to that in my previous in my previous videos, that this is called a non-directional testing hypothesis. You're not taking side whether it's going to be greater or smaller. All you care for is that it's not equal to 100. All right, step number two, you're going to pick a probability, that's the alpha, below which your probability is going to be small or big. We call this alpha, and if nothing else, we're going to say it's 5%. Okay? Whenever you're going to pick 1% or 10%, I have to say something to you so that you pick something different than 5%. Okay? Of note, alpha is also called a type 1 error, but we'll come back to that in a different lecture. Don't worry about it for now. So we set alpha and we assume that the null is true. Now we need to calculate the test. Now, which test are we going to calculate? Is it going to be the Z or the T? Well, you know already that the difference between the Z and T is whether you have sigma or you don't have sigma. If you have sigma, you go with the Z. If you do not have sigma, you go with the T. But you have to remember that the T has degrees of freedom. Okay, now, how do you decide? Well, it's going to depend on your results. What are your results? Well, in this situation, we were able to get a sample of 16 individuals on the pump, and their blood pressure average was 115, so the X bar was 115. And here again, we are willing to use a sigma of 30. The minute you hear sigma, you should know that we're going to use the Z. But before we continue, you have to notice that your sample size is less than 25. Therefore, the central limit theorem is not automatically normal unless the blood sugar, the original variable, blood sugar, had a normal distribution. So we need to make this assumption as well, or we have to make this declaration that blood sugar has a normal distribution. Then the sampling distribution of the mean is normal, and therefore I can start using the Z. So I calculate the Z. Now this time, notice the Z came out to be a positive value. It's a +2. I say this because you need to know that for the next move, which is the p-value. Okay, so the p-value, if you remember what is the p-value, is the probability of observing results that you observed, or even more extreme, under the condition that the null is true. So it's the probability of getting results as extreme as the one that you observed, or more extreme, under the condition that the null is true. So that translates into the P of Z greater than 2 or less than negative 2. Okay, as extreme as you have to take both sides. Or you can just take probability of Z greater than 2 and you multiply it by 2. If you do that on your Z table, you're going to find that the area is 0.0228. Don't forget that you need to multiply it by 2. So you get an area of 0.0456. That is your p-value. So your p-value is 4.56%. It's still less than 5%. Okay? So remember, if your p-value is less than alpha, you're going to reject the null hypothesis. If your p-value is greater than or equal to alpha, you're going to fail to reject the null hypothesis. And remember, this is called the statistical conclusion. Okay? All right. So that takes us to step number 7. So we rejected the null hypothesis based on what happened with the p-value, and therefore you're going to say something about a pump, remember? What are you going to say? Well, you're going to say that we have evidence that the pump does not maintain the blood pressure, the blood glucose at 100, since we rejected the null hypothesis. So are you going to say that the blood sugar is greater than 100 or less than 100? So is the pump actually letting the blood sugar being too high or too small? How do you know that? Well, you're going to know that by looking at the results obtained from your sample. The results obtained from the sample was 112. The X bar was greater than 100, and therefore you're going to conclude that it's going to be greater than 100. So in our example, we have evidence to reject the null hypothesis, and thus we can say that the pump is not doing what it was claimed to be doing. Notice that I use the word evidence and not the word proof. In statistics, we do not prove anything because a proof is a mathematical proof. Okay, x plus 1 equals 2, x is equal to 1. That is a proof. But in statistics, we're basing all our work on probability. We do not prove anything. We just have evidence. But that's actually acceptable and it's quite good. Had we failed to reject the null hypothesis, let's suppose the p-value came out to be equal to 0.814. We would say that we did not have evidence to reject the null hypothesis, and therefore we would have to accept the claim that the pump maintains a blood sugar of 100. Okay? So here's another example. Do cars made before 1985 have a CO exhaust greater than the accepted level of 120 ppt? Again, notice that the null hypothesis is mu, so I'm using a population parameter, and it's equal to 120. Again, why equal 120? Because remember, the null hypothesis assumes innocence, so it takes things as at their face value. We're going to start with, let's say that the cars are innocent. It means that their exhaust is at the accepted level, which is 120. The alternative hypothesis, mu of CO of those cars made before 1985 is not equal to 120. Okay. Step number 2, you're going to set alpha at 5% and you're going to do a test. All right, so this time I'm going to do a t-test. So let's suppose I was able to obtain 9 cars. The sample is 9. I calculated the average CO and it came out to be equal 132, and my sample standard deviation is 18. Before I continue and before I calculate a t, I have to ask myself, can I make the assumption or can I say that the sampling distribution of the mean is normal? Since my sample size is less than 25, I would have to go back to the original variable. Here it's the CO concentration, and I have to say that CO concentration has a normal distribution. Having said that, I can carry on. I can say, okay, now I can trust that the sampling distribution of the mean is normal, and therefore I can either do a Z or a t-test. The choice of using a Z or the t-test lies in whether you have sigma or not. In that specific example that we have here, we do not have sigma. We have the sampling standard deviation S. And therefore, we're going to use it, and you're going to calculate T. T came out to be equal to 2, according to this calculation. Remember, T has a degrees of freedom, which is N minus 1, which is 9 minus 1 is 8. Okay, so that is step number 3. So the T that I calculated came out to be equal to 2. The next step is for us to get the p-value. Remember, the p-value is as extreme as. Since t came out to be positive, the as extreme as, you have to go towards greater than 2. If t was negative, you'd have to go below the negative 2. Okay? So what you're looking for is you're looking for the probability of t greater than 2, and you have to multiply it by 2. Remember, because it's a two-sided, we need to multiply it by 2. So you're going to go to your t table for degrees of freedom 8, and you're going to start looking for 2. If you do if you look it up correctly, you're going to end up not finding 2 for degrees of freedom 8. You're going to find 1.8595, and you're going to find 2.036. And therefore, you're going to say that your probability that you're looking for is limited by these two probabilities. Okay, notice I'm multiplying by 2 each time. Okay. Now, I'm not going to go over the fact that this is greater than a positive number, and then you have to do the 1 minus. You already know how to do that. This is just something that we've covered before. All right, so you end up with your p-value being captured between 5% and 10%. So definitely p-value less than 10%, but definitely greater than 5%. So that takes you to step number 5, where you have to compare your p-value to alpha. Now, knowing that your p-value is definitely greater than 5%, so you kind of know that definitely your p-value is greater than alpha. Therefore, you go to step number 6. Since your p-value is greater than alpha, you're going to fail to reject the null hypothesis. And then you're going to reach the conclusion that there's no evidence to suggest that cars made before 1985 have an exhaust different than the allowed amount of 120. And therefore, we're just going to have to accept that claim. Please notice that when I'm writing my research conclusion, I'm saying we do not have evidence. And I'm also taking back the conclusion to whatever population I was studying. The population I was studying were cars made before 1985. It wasn't just cars in general, okay? You have to be specific to the population that you're studying. So we're going to stop here with the introduction of testing hypotheses, because next we're going to deal with what if we had a proportion.